Today we are going to look at more applications of derivatives. Let's take a look at this question, for example. Growing sand pile. Let's read the question. It says, sand falls from a conveyor belt at the rate of 10 meter cube per minute onto the top of a conical pile. The height of the pile is always 3/8 of the base diameter. How fast are the height and the radius changing when the pile is 4 meter high? Give your answer in centimeter per minute. So first of all, keep in mind when you're solving such kind of problems, the crucial thing to do is, understanding the problem is the utmost important thing for you to do. So read the question one more time and try and comprehend the question completely and understand what information is provided, what you're trying to solve for, and what is the moment in question. All those kind of things you need to understand. So let's read the question again. It says sand falls from a conveyor belt at the rate of 10 meter cube per minute. So that's a key information here. 10 meter cube per minute. It tells you the rate at which the volume of the sand is being added to the conical pile. So the volume of the conical pile is changing at that particular rate. So we know dV by dt is given. This volume is, increasing every time, so it's positive. So we say 10 meter cube per minute. That's given information. The height of the pile is always, it's a key word, it is always 3/8 of the base diameter. So that's another key information. If h stands for the height of the pile and d stands for the diameter, we can represent that, using h is 3/8 of the diameter, or if you want to put it in terms of the radius, h is 3/4 of the radius, because d is twice r, so 2 times the radius, so h is 3/4 of r. Okay, let's move on. How fast are the height? How fast are the height and the radius changing? So what is the question asking for? How fast is the height changing? How fast is the height changing is nothing but the derivative. The rate at which height is changing is dh by dt. We want to know that. And we also want to know how fast is the radius changing. That means we are looking for what is dr over dt. And at the moment when the pile is 4 meter high. So this is the moment in question. At the moment when the pile's height is 4 meters, we want to know what is the rate at which the height is changing as well the radius is changing. Now the question also gives us another thing. It says give your answer in centimeter per minute, so we want to pay attention to that. And so if you would like to immediately convert your height information into centimeters, you could go ahead and do that. It's 400 centimeters. Similarly, the rate at which the volume is changing in terms of centimeter cube per minute will be 10 times 10 to the 6 centimeter cube per minute, or you could say 10 to the 7 centimeter cube per minute. Okay, so now so we have written down the given information. We also have identified the moment in question, which is this, right? We have identified the moment in question. Now let's just go ahead and draw the diagram. So it is a conical. We don't even, if you understand the question, if drawing a diagram is helpful, you could always draw the diagram. And it says that the height is always, 3/8 of the radius. So r is the radius and h is the height. That much we know. Now I think since we know the rate at which the volume is changing, how do we relate the volume, the height, the radius of a cone, of a conical pile? So we know the volume of a cone is 1/3 pi r squared h. So first, beginning with a mathematical model that gives the relationship between volume, height, and the radius of the cone, would be the appropriate thing to do. Then let's talk about what is the rate at which, each of these are changing. What is the derivative? So implicitly differentiating the entire equation. So dV by dt, since 1/3 pi is a constant, let's take out the scalar and differentiate r square h using, using the product rule. So if you say 2r dr by dt times h plus, keeping r squared constant, the derivative of h with respect to t. So it is, now that we know h in terms of r, it would be ideal to just express, h, wherever we see h, we can replace it with r, 3/4 r. So this would be, in other words, 1/3 times 2r times 3/4 r for h, and then dr by dt plus r squared times, we don't know what is dh by dt, but if you can go back here, if h is 3/4 r, that tells you that dh by dt is 3/4 times dr by dt. So you could use that. So substituting here, 3/4 times dr by dt for dh by dt. Now you have the equation for dv by dt completely in terms of a single variable, that is r, and also in terms of its derivative. So dr by dt seems to be a common factor, so we can factor that out. So dr by dt times, we had a 1/3 pi actually. I missed out a pi over here, so let me write that down. So we have a dr by dt times 5/3 times, if you can put it in a simpler form, it is 2r squared times 3 divided by 4. In a simpler form, it would be 3r squared over 4, plus here we have 3r squared divided by, I'm sorry, this should be a 2, I'm sorry, it cannot be because you cancel out the 2 with the 4. It should be 3r squared over 2 plus 3r squared over 4. So if you can, take the LCM and then simplify this expression further, it simplifies to, 2, so 2 times 3r squared, it's a 6r squared plus 3r squared becomes a 9r squared divided by 4, and that's what you have. And simplify further, 3 and 9 cancel out, so you have a 3r squared pi, 3r squared pi divided by 4 times dr by dt. You have a simple expression for dv by dt. Now that you know what is dv by dt, you know what is dr by dt. No, you're looking for dr by dt, if you can figure that out. At the moment in question, it says h is equal to 4 meter is the moment in question. And we want to be able to, say, what is r. So we know that at the moment in question, we have h as 400 centimeters. And we also have the relationship between h and r as h is equal to 3/4 r. Now if you can substitute for h as 400 centimeters, r will be 4 times 400, which is 1600 over 3 centimeters. So now what we can do, we can plug in the value for r into that equation. We can also plug in the value for, so we can substitute for r as 1600 over 3 centimeters into this equation for dv by dt, and we will have then, substituting for dv by dt as 10 to the 7. If you can go back and see here, we had said earlier that dv by dt is 10 times 10 to the 6, which is, in other words, 10 to the 7 centimeters cubed per minute. We'll just disregard the unit for the time being. 3 times 3 over 4 pi, let's say, factor that out. R squared will be 1600 over 3 squared times dr by dt. So if we want to simplify this first, you could say 3 and a 9 here. 3 squared is 9, so that will cancel out, and you will have a pi over 4 times 3. And this will be 1600 squared. For simplicity, I'm multiplying 16 squared and saying 256 times 10 to the 4. So I would be able to do the cancellation easily. So what do I have? I have a 10 to the 7 equals to that. Looking at 10 to the 7 on the left hand side, 10 to the 4 on the right hand side, we can cancel out at 10 to the 4 from both sides. So 10 cubed is equal to pi over, if you want to do the cancellation here for 4 times 3 and along with the 256, so let's say 4, you can cross out 4 with the 256, so it would be 64 times. So 64 pi divided by 3 times dr over dt. And if you can just solve for dr by dt from here, that would be a 3000 divided by 64 pi. Both are even numbers, 3000 and 64. So we can see if this would be a 1500 if you want to go for division by 2, cancellation by 2. That would, I think, it is further divisible. We could have easily gone for division by 4 instead. I'm just doing it step by step. So 8 pi, I'm sure 4 divides into 150. So if you say 3 times 4 is 12, 337, 375 over. So dr by dt, we found out the rate at which the radius is changing, though part A was finding the rate at which the height was changing. We figured this out first, and it is centimeter per minute. Now you go back, we have this relationship between h and r established, and we also said that dh by dt is 3/4 dr over dt. So we are going to bring that connection back between h and, so dh by dt is 3/4 times dr by dt. In this, we substitute for dr by dt as what we found just now. It's 375 divided by 8 pi centimeter per minute. We'll consider the unit at the end. So this would be 32 pi in the denominator. 4 doesn't seem to cancel out with 375 or with 3. None of those, there is no common factor here, so that can be used to eliminate, do the cancellation. So it should be 1125 over 32 pi. It's centimeter per minute. We are finding the rate at which the height is changing. Height is expressed in centimeter, the rate at which it is changing. So the appropriate unit would be the unit of height over the unit of time. So it is centimeter per minute. And we found out both how fast the height of the pile was changing, and also how fast the radius of the pile was changing. And this is what we were supposed to find, and we found it. And at the end, we always, please make sure that you interpret the answer by writing a sentence. Okay, hope you understand it.